To prevent that, we place rocks to dissipate the energy. After the flow goes into the energy dissipators, it evenly spreads out into the bioretention cell and then goes down the media, filters through the media, and then it collected into the under drain pipes. This structure serves two purposes. Number one, in events that you have larger storms, the water builds up and it all flows into these outlets. Number two, the treated water that is collected from the under drain drains into this structure.
The media is a very important component to the bioretention. Typically, the media is about 50% sand, 30% organic material, 20% topsoil, all of this by volume. And this media has been found to be very effective in managing the water quality and the hydrology. What we have here is an ongoing experiment. This is a column loaded with sand that contains iron oxide as a coating. The iron oxide coating will assist in the removal of bacteria from runoff that will pass through. What we hope to do is to use this as an additive to bioretention and rain garden media to assist with the removal of bacteria and pathogens. This is a research bioretention site on the University of Maryland campus. It's a linear site that manages runoff off of this roadway. We have monitoring equipment set up so that we can monitor both the flow and the water quality coming into this system as well as coming out to completely evaluate the improvement due to the bioretention.
So this site's been here for a couple of years now, and you can see someone has really maintained the vegetation and kept a really nice mulch layer on it. But what we really want to do is see how the soils are progressing. Now, when we put this bioretention soil in during construction, it's a very consistent kind of mixture. And that what should be happening over time as the soil evolves, as you have more organic material from the leaves and the mulch entering, you start to develop a soil horizon. And so what we want to do is kind of clear away a little bit of this mulch and get down and see what the soil looks like. So here, actually, on the very surface couple of inches, top couple of inches, this really isn't a good sign. Probably what happened here during construction is some sediment from the site. Maybe a site wasn't totally stabilized, and some of the sediment probably washed down on top of the soil layer before it was mulched. And you can see here that sediment contained a lot of clay, because if you can do this with the soils, it means it's not going to really drain very well. You can see here lots of clay because you can form a ribbon with it and it stains your hand. So let's dig down a couple more inches and see what we can find in the soil. Now what you see is probably really the bioretention soil mix. And you can see here a lot of sand, just a little bit of dark area from the organic material that was put in, and the topsoil. And this will drain very well. You can see it's very friable and really falls apart in your hand.
I'm here next to the Benning Road Bridge and roadway, where stormwater coming off this road flows into this catch basin and is directed through a pipe to the bioretention cell to my left. Several years ago, I monitored this site for the 20 water pollutants in stormwater. We measured total suspended solids, all the different parameters of solids, nutrients, heavy metals, and organics, to evaluate how well this site performed in comparison to sites throughout the city at other locations. Other than overflowing, the site worked perfectly like all other bioretention cells that I've monitored in the city. Bioretention cells have shown enormous capability to remove many nutrients, heavy metals, and pollutant parameters that normally end up in our natural water bodies that other devices show no capability to remove. A normal catch basin does not remove any of the nutrients that cause eutrophication and the degradation of our waterways, while these sites that have natural vegetation that can perform evaporation, transpiration, lowering the total amount of water that reaches the river, and also absorb nutrients and heavy metals that normally would be reaching the waterways.
This soil is kind of an unstable soil. We're going to have to rebuild it. That ensures that it doesn't continue to cut and fill in.